Hello and welcome to my course, Transformation, Semigroup and Applications. I am Dr. A.T. Imam, a senior lecturer at the Department of Mathematics, Ahmad Bello University, Zaria, Nigeria. This is a lecture of the series. In this lecture, we are going to start talking about transformations, semigroups. So the outline of the lecture. So this is the first chapter of the course that covers transformation semigroup. And in the first section of this chapter, we are going to talk about definition of a transformation of a set, and then we will also talk about the full transformation semigroup. So, and the structure of a full transformation. However, in this particular lecture, we are only going to talk about the first two components of the chapter, the definition of transformation of a set, and we'll also talk about the full transformation semigroup. In the second lecture, we hope to discuss extensively the structure of a full transformation of a set. So we start by defining what a transformation is. So given a non-empty set X, a transformation of the set or partial transformation. A transformation is also called partial transformation of the set X is just a mapping alpha from A to X, where A is a subset of X. So once you have a map from a subset of a particular set into the set, and that is what we call a partial transformation of the set. And then the set A is called the domain of the mapping, and we denote it by dom of alpha. If the domain of alpha is equal to X, then alpha is called a full transformation. So this is the difference between the definition of a partial transformation and what we call a full transformation. So by the very definition, we can now see that every full transformation is also a partial transformation, because if equality happens here in defining the partial transformation, that is, if the domain is the entirety of the set X, then the partial transformation becomes a full transformation. But however, not every full transformation is also a partial transformation. For example, if we take a set of 6 elements, 1, 2, 3, 4, 5 to 6 elements, then we can visualize a mapping or a transformation, a partial transformation of the set Xn as this, where we can view the set Xn at the top, and then below it we have the set again, and we'll be mapping element from the set X down to the element in the same set. So a partial transformation may be such a mapping sending 1, 2 to 4, and also mapping 3 to 1, sending 5 to 2, and 6 to 4. So this is an example of a partial transformation. You have a set and the set is set. So the domain of the map is actually a subset of the set, because we can see that here 1 is not mapped to anything down, and 4 is also not mapped to anything down. So 1 here is not a member of the domain, and also 4 here is not part of the domain. So this is a clear example of a partial transformation, and it's not a requirement that every member of the codomain must also be an image, because we can see that 3 here, 5 and 6 are not part of the images. Only 1 is an image of 3, and 2 and 4 here becomes images of some element in the domain of the mapping. So we have the domain of this map is 2, 3, 5, and 6, and then the images are 1, 2, and 4. So this is a partial transformation, and so therefore it's not necessary when we are visualizing a partial transformation, since the domain is 2, 3, 5, and 6, we don't have to visualize elements that are not in the domain. So we only pay our attention to members of the domain, and so therefore we don't look at things that do not appear in the domain, because our attention is just the domain. You know, in a mapping, you require that every point of the domain must have an image in the codomain. And we also look at only elements that belong to the image set. So we don't see 3, 5, and 6. We only look at 1, 2, and 4. So this is how we generally visualize a partial transformation. And we are looking at the domain of the map, so not the set X. So therefore, this is actually DOM alpha and not the entire set. And down here, we are also looking at only the image of the mapping and not the entire set X. So this is the image, and this is what we write for the image of the map. So only points that appear to be the result of transforming some element from the domain into the set X, and these are called images, and we donate the entire set by Im alpha. And then one thing we can observe is that here 2 and 6 are mapped to the same point 4. So 2 and 6 mapping to the same point 4 means they are together in the sense that they have the same image. And so therefore, in visualizing a partial transformation, elements that are mapped to the same point, we put them together as a group. So therefore, we see 2 and 6 as one group, and so we use only one arrow. That entire group of the point 2 and 6 is mapped to 4. And 3 is seen as a group consisting of only one element, and it is mapping to 1. And 5 is also seen as a group mapping to 2. And then we can also rearrange, because the order here in which we arrange 1, 2, and 4 is not very necessary. So we can rearrange. We can write the image of 2 and 6 directly below it, and the image of 3 can be written directly below it. That is 1 here. And you can also write the image of 5 directly below it. So it's easier to visualize the mapping like this, so that the element that a block mapped to is directly appearing below that block. And in doing so, that means the when you are doing visualizing it like this, then we can now see that a partial transformation is actually partitioning the domain into subclasses, subsets. So you can see that we have a subset here that map to an element, and another subset here mapping to a particular element 1, and a subset here mapping to. And when you take the union of all of this set, you get what is called the domain of the mapping. So actually, generally speaking, a partial transformation is visualized as this. The domain is a partition of set A1, A2, A3 up to as many subsets as are involved in the partial transformation. And the union of all the subsets is what we call the domain, what will constitute of the domain. You can have as many, up to infinitely many of them, depending on the size of the domain. And then down here we have a single element, a B1, B2, B3, and this single element, the set of all these elements, constitute of the image of alpha. And this is how you see it. A1 is mapped to B1, and A2 is mapped to B2, and A3 is mapped to B3. So therefore, generally for every I greater or equal to 1, we have alpha sending the block AI to the element B1, and this BI, and this element BI is a member of the image. So this is how we visualize. And it is not necessary actually, if you understand the notation, that every block is mapped to the point directly below it, then writing the arrows is not generally necessary. And so therefore, in general, in an array form, we write a partial transformation as in a form of an array, where we have 2 rows. The first row consists of the partitioning of the domain A1, A2, A3, and the second row consists of partitioning of the or listing the element of the image set B1, B2, B3, where at every block the point appearing directly below it is the image of that block. And so therefore this notation is very pronounced, and it's self-explanatory, and it simplifies the way we visualize a partial transformation. And once we visualize a partial transformation in this way, then we refer to the blocks or to the partitions. A1, A2, A3, members of the partition A1, A2, A3, this subset are called blocks of the map alpha itself. So we say a block of alpha is a group of elements that are mapped to one point in the codomain or in the image set of the map. And then the set B1, B2, B3 you have already introduced is called the image of alpha, and it is denoted by Im alpha. In fact, we have seen this notation over here when we are trying to understand how we can visualize a partial transformation. So for each y in the image set, we write y alpha inverse, and y alpha inverse will be the set of all points in the domain that are mapped to y. That is, the image of x under alpha is equal to y. So this is the notation we will continue to be adopting. We are going to write argument or mappings at the right of the argument. So instead of the usual convention at the secondary school level, we write f of x, or in calculus we mostly write f of x. We write f of x like this, and then we write x in the but instead of writing f of x or alpha of x, we write x before f, so that we pronounce it as the image of x under alpha instead of saying f of x. So this is the notation we are going to adopt throughout this course, and then we'll be writing like this. So this is the image of x under alpha. So all elements that are mapped to y will be grouped together, and we will use y alpha inverse as the notation for that particular set. And from the very definition of this, we extend by whenever we take a subset y of the image set, then y alpha inverse, so this is a subset now of the image set, so y alpha inverse will be a notation for the set of all element of the domain that are mapped to some element in y. So this will be a union of all y alpha inverse, where y is an element of the capital Y here. So this is actually generally the notation we are going to adopt. But then from this very notation, we can see that this y alpha inverse for every y in the image set, y alpha inverse is nothing but the block. It is this block, because if you look at B here, you know, if you are looking for the set of all elements that are mapped to B, is actually this A1. That are mapped to B1 is A1, and the set of all elements that map to B2 is exactly A2. And likewise, the set of all elements mapping to B3 is exactly A3. So generally, for every I, Bi alpha inverse will be equal to Ai. So this is another notation. This particular notation here is just another notation for the blocks of alpha, with making reference to the image that the block is mapped to. So, and for example, if you take y to be the set of B1, B2, then you are talking about A1 union A2. So I can take a group of images and then look for this set of all elements that map to these images, and it will be actually the union of the blocks that map to the images. So this is a standard way of seeing a partial transformation of a particular set.